All right, folks, can you all hear me? Awesome. Okay. Thank you very much for coming out today. We really appreciate y'all's attendance and your time. We're here at reInvent to do this for you, so I hope you take something out of it. My name is Ben Clay. I'm a developer with Amazon DynamoDB, and today with Brett McCleary from Precision Exams, I'm going to be talking about building high-scale, high-performance applications on top of DynamoDB. In the first half of this talk, I'll give a series of best practices towards building scalable data models on top of DynamoDB. In the second half, I'll hand over to Brett McCleary with Precision Exams, and he'll talk about how his organization is architected on top of DynamoDB, and in particular, how they've done load and performance testing. So the outline for my half of the talk is as follows. First, I'll give a short background on why we built DynamoDB, what it is. Then I'll give a little primer on how we scale under the covers, because it's very important to understand what we're doing with your data as we scale you so that you can take advantage of our capabilities. Then I'll go into sources of application latency. What is standing between your application when you're making a request to DynamoDB and your data as it lives in DynamoDB? Then I'll go into these best practices, talking about how you can design your data model and your access patterns to get the most out of us, and then I'll hand over to Brett. So first, real quick, why did we build DynamoDB? When we started to design DynamoDB, we went to our customers. We saw a need in the market, but we surveyed our customers to see what they were really looking for in a next-generation NoSQL database. They really wanted reliably low latency at any scale. This is typically an area that relational databases fall over with. As you scale them out horizontally, latency takes a hit. They also wanted elastic throughput and storage. They wanted to be able to scale these two factors independently, dial them up and down as their business needs changed. They wanted flexible queries, flexible data models, strong consistency, and above all, they wanted really good availability and fault tolerance, because this is a database product, and not only would they store their data in it, but they want to store their own customers' data in it. So this is very important. So in response, we built and have iterated upon DynamoDB. It's a fully managed NoSQL database service. It consistently gives single-digit millisecond latency. It scales in, throughput and storage independently. I'll talk about that a little bit more in a minute. As of October of this year, it supports both document and key value data models. And it uses automatic data replication across 3 facilities to give very good availability and fault tolerance characteristics. So briefly, I want to give a primer on how we scale under the covers. This is a 400-level talk, so I'm assuming that most of you know this, but it's very important that everyone's on the same page in this regard. So very briefly, we scale for size and throughput independently. If you put more items in your table or you ask for more IOs per second, we respond by partitioning. We cut your table into pieces, and we spread these pieces across more and more physical hardware. It's classic horizontal scaling. When we do this, we chop the provision throughput on your table equally amongst the partitions. So in this little toy example, we have a customer that's asked for 1,500 writes per second on his or her table. We've, in the background, cut it into 3 partitions to meet these throughput or storage demands. And so every partition gets 500 writes per second. Simple, right? Now, talking about accesses and partitions, every item in DynamoDB has a hash key. When you define a table, you tell us, this is my hash key attribute, and this is my range key attribute. The rest is schemaless, but every item must have those fields. The hash key is super important because this determines not only what partition this item will live on, but where in that partition. You can think of every partition as a discrete key range. Every partition has a start key and an end key. So when you hand us an item or ask for an item, we look at that hash key and then figure out which partition this item is going to live on. So putting these 2 things together, the fact that every partition gets equal throughput, an equal slice of that pie, and the fact that every hash key maps to 1 partition exactly, we really need you to spread your workload uniformly across your key space, because that spreads it uniformly across the partitions. Now, we don't require you to do that. You don't have to. We have plenty of users that have non-uniform workloads. But if you can spread evenly, you can really take advantage of our scale. If you have what we call hotkeys, these are keys that are overpopular relative to their peers. And what happens is the partition on which that key lives gets really hot, and the other ones are cool. And because you paid for provision throughput and we've chopped it equally, those cool partitions, you're really not getting your money's worth. So why is this important for latency? Why does this matter for performance? Before we go into these best practices of how to architect around this problem I've been alluding to, I want to go through some of the sources going down the stack. Where can your application get slowed down talking to DynamoDB? So there's 4 sources I've got here. I'll just breeze through these pretty quick. Resource availability, then moving down into network behavior, what's going on in your application, the SDK, the OS, provision throughput on your table in DynamoDB, and then this heat skew problem that I was just mentioning. So if your application doesn't have enough resources, you're not going to be able to push performance to DynamoDB quick enough, or push requests, I should say. You might get good performance most of the time, but it's those high percentiles, you're really not going to get the latency that you want. So of course, node hardware comes into this. You got to make sure the box is big enough for both your application and all the work it's doing to talk to DynamoDB. You know, another facet on the same problem is workload colocation. If you stuff too many workloads in the same box, the application that you're trying to optimize is not going to be able to move quick enough. If you use a managed language like Java, we see a lot of customers have trouble with heap size and garbage collection. Definitely dial up that heap size. It can start hurting you after a point, but please play with it and see what kind of performance you get. Garbage collection is another aspect of the same coin or side of the same problem space. If you are noticing odd pauses, definitely check out GC. You don't need to necessarily understand your garbage collection algorithm. Just look at your GC metrics and correlate them with performance problems and see if they line up. GC in particular can throw odd pauses even in metrics. So if you're trying to dig into this problem and you're seeing latency spikes or spikes in a certain metric, you might have seen a GC pause while that metric was being collected. It's a nasty little gremlin, so make sure that you're accounting for it. And finally, context switch overhead. We're finding that people are using thread pools more and more. They're dialing up these thread pools as their core counts go up. That's great. But just like heap size, don't go too far, because otherwise your CPU is going to spend a lot of time context switching. So moving down the stack into network-related behavior, this is a grab bag of anything that's network-related north of the DynamoDB endpoint in this little figure. Connection pooling is a huge one. Make sure you're amortizing the cost of setting up a connection. DynamoDB gives consistently single-digit millisecond latency. Setting up a connection is far more expensive than this. So make sure that you amortize this sunk cost across a lot of requests. It's turned on by default in the SDK, but make sure it's turned on. And there are other application models that don't map well to connection pooling. The classic example is in Apache. If you're forking processes to serve user requests, when that process gets reaped, it's going to throw away those connections. So definitely try and take advantage of this. SDK auto request behavior is another. I'll talk a little bit more in detail about this in a minute, but the classic example is retrying throttled requests. SSL overhead is another. SSL is not free. Make sure you're accounting for it. And then, of course, round-trip time and packet loss. When we all think of latency, we're thinking about network fabric problems. They do exist, but they are just a piece of this puzzle. So moving down into DynamoDB, insufficiently provisioned tables look like latency to your application. And why is this? It's because you hand off to the SDK, you say, please put this item in DynamoDB. The SDK will try and go to DynamoDB multiple times. It gets bounced back with throttles. The default behavior is to retry throttled requests, and then it will finally come back up after 3 or 4 round trips. That looks like latency to your app because it handed off the request, and the request just took a while to come back. So we do allow you to go above your provision line for a short period of time. We call this feature bursting, but it's for short temporal spikes. It's to take the sharp edges off a bursty workload. It's not for chronic under-provisioning. So if you look at CloudWatch and you see yourself bumping up against that provision throughput line, definitely just dial up and you should see a decrease in your application latency. Finally, data model and table growth, and that's what I'm really here to talk to you about today. If you are accessing only a subset of your key space, or a subset of your key space is quite hot relative to the rest of your key space, as your table grows, this is going to become more and more apparent. Because again, as we add more partitions, you're accessing a subset of those partitions. This will never appear when you have one partition. It's because that one partition has 100% of your throughput. It's a small table. But as you scale and you access fewer and fewer of those partitions, what's going to happen is you get throttle responses back, but you look at CloudWatch and you're nowhere near the line. So this is what I want to talk about today. How can we design around this when we're building our tables, we're thinking about our access patterns? So I'm going to dive right into it. The first best practice is combining queryability and uniformity when you do your key selection. It's a mouthful, but it's a very simple idea. And the toy use case I'm going to use throughout this presentation is Webster order processing. Let's say that you run a web store, and in particular, you want to do your order processing on top of DynamoDB. You like its availability, its fault tolerance, its speed. So you've chosen DynamoDB, but we've got some problems to kind of work around. So in this example, we'll have two toy workloads. The write workload is placing orders into the table, just writing items into the table. And the read workload is building up a single customer's order history. We've all gone to an online retailer of choice, and we wanted to see what we purchased in the past. So that's our archetypal read workload here. In the upper right, you can see a schema that satisfies this pretty well. It has a hash key of customer ID and a range key of timestamp. This schema is super easy to query and paginate. The query API in DynamoDB requires that you know the hash key. In this use case, you will know the hash key because this customer is logged in, gone through authentication. As part of that, you've looked up their customer ID. In addition, this range key of timestamp lets you sort the results and paginate them as they come back from DynamoDB. So you could say, give me all the orders going back in time and paginating by a page size of, say, 10 or 15 or 25. Then as the customer clicks the next page button, you reissue that paginated query to DynamoDB, re-render the web page, and shove it back to their browser. In addition, what's great about this schema is that the read and write heat is well spread. The average customer of yours for your web store is going to place 1-2 orders a day, and they're going to build up their order history once or twice a week, a few times perhaps. Even the far upper percentile, let's say your most power user, is like a bulk wholesaler. It's hitting an API, it's not hitting the website. And at 9 a.m. or 5 p.m. Eastern, they dump 5, 10, 20 orders on you at the end of their day or the beginning of their week. When this happens and you have this burst of heat to that customer ID, those items are going to be small. This is text we're talking about. It's not large binary data. DynamoDB now supports 400 kilobyte items, but these are just a few kilobytes. So every order is only going to consume a few writes per second. So although it's not strictly uniform, it's got enough uniformity that you're going to skate by. So again, the theme throughout this talk is that selecting your keys well, making sure that heat is well spread, will let you scale with us. And to do this, you really need to select keys that are both queryable and uniform. You need to be able to access your data in a way that makes sense for your business, but you also need to spread those accesses evenly across the key space. And this is important when you're designing high-growth tables, because that's when this is really going to start to bite you at the exact moment when you need your database tier to scale, and that's when your business grows. So best practice number 2 is taking these lessons learned and applying them to indexes. So what if we have an alternate query pattern? We want to query the same data, but we want to use a different hash and range key. DynamoDB has a feature that we introduced last year called global secondary indexes that allow you to do this. So one workload that would, or one query pattern that would work really well in this use case is household ID. We want to associate multiple customer IDs under a single household ID, and we let a member of the family look at his or her household's purchases going back in time. So if the item has the hash key and the range key for the index, DynamoDB, when you write it to the table, will look at that item, will say, yes, it does have everything it needs, and we'll handle the index propagation for you. So under the hood, the way that this works is, you write to the table, we look at it, we push it to the index asynchronously, and then you can run read clients directly against that index. But the interesting thing about this is that global secondary indexes are partitioned independently from the table. So let's look at an anti-pattern that exposes why this is very important to consider. What if we want to query orders from last month? We want to do inventory projection, some kind of analytics. We might look at month and realize that that's a terrible key. There's only 12 of them in a year, January, February, March. But what about day of order? We could use day of order, it has high cardinality, and then we could issue queries for every day in last month to build up this corpus of data for us to do our analysis with. So let's try that. What happens when you do that is that although the write heat on the table itself is well spread because it's keyed on customer ID, The heat on the index is terrible. It's all concentrated on one partition because every time you write a new order to the table, we propagate it to the index and the hash key changes from customer ID to day of order. And all the orders from today are going to land on, therefore, the same hash key. When this occurs, that partition in the index gets hot. And so it's going to start throttling. And when we notice it throttling, we're going to have to start throttling you on the table. Because you can think of this like a pipeline. We have to keep the pipeline moving. We can't keep so many balls in the air. We can't keep juggling past a point. We do have some flex here, but not a whole lot. So at that point, you're going to start seeing throttling on your table. So the takeaway here is that index keys behave just like table keys. The mechanics are identical. All the rules are identical. And this is important when you're indexing a high-scale table. We recently pre-announced online indexing. It's the ability to turn on global secondary indexes for existing tables. If you have a high-scale table and you've been just waiting to turn on that index, that's great. We've worked very, very hard to build this feature for you. But do be careful when you select your keys, because the right uniformity of the table is actually going to be a min function of the right uniformity on the table and all of the indexes. So the more indexes you bolt onto this thing, you need to think about the key selection, or otherwise you're going to see this throttling where it wasn't there before. So best practice number 3 is pruning frequently scanned tables. So let's say we still have this same workload. We still are trying to get last month's orders, and an index didn't work in this use case. So we could just scan the whole table and look at every item and say, was this in last month? Okay, well then we'll go do our analytics on top of it. And scan is actually not a dirty word in DynamoDB. We can scan all your partitions in parallel. So for wall clock time, we can actually make it quite fast. But it does get more expensive over time. Think about it, you have a fixed number of needles, all the orders in last month, and the size of the haystack just keeps growing because you keep adding more and more months' data to this table. So one naive response to this is we could control this table growth with deletion. We could look for old orders, we could archive them somehow, and then we could delete them out of the table. So the real takeaway here, even though this is a very simple technique, is that table growth impacts throughput per key. And this is important when you're accumulating infrequently read data. Because again, the use case and the assumptions that DynamoDB was built for is that you're accessing all of your hash keys in a roughly uniform manner. But if you're storing old data in that table and you're accessing that less frequently, you're violating that assumption. And we don't care. We'll let you continue doing that all day, but it will end up biting you as those colder, older hash keys accumulate and pile up and dilute the throughput per key on your newer keys, your newer orders. So there's actually another technique, if you can make it work for your application and for your model, that works even better in this space. It's called table rotation. Now the real problem with deleting items from the client side, if any of you have done this before, is that it actually doubles your write cost. You pay once when you write the item, and you pay again when you delete it. So there's a way to achieve cheaper deletes and scans here, and that's called table rotation. That's what we call table rotation. It's an unofficial term. If you have a table for discrete time periods, then it gives you a lot more control over the situation. In this case, we would have one table per month. So this gives you 3 primary benefits. The first is that now that scan to look at all of last month's orders is super efficient. Every item in that table is relevant to the query. Now the number of needles is equal to the size of the haystack. That's awesome. Second is deleting whole tables has no throughput cost. Because when you nuke a table, we go clean it up in the background, you stop paying immediately. There's no more of this double pay, once when you write, once when you delete. But the third and actually most powerful benefit is that now you can dial up and down every month independently. So what's the chance that you're going to write an order in last month's table? You might go amend somebody's order, but I mean, that's going to be pretty rare. You could probably drop that writes per second down to 1 or 2 per second. I mean, you can really push that to the floor. The other thing you can do is as you accumulate these tables going back in time, you can drop their read throughput down. Because you're going to have some customers that are going to want to look at their orders from 2011, but that's a rare customer. Most of them are going to be looking at this month. So that way you can have this month's table be dialed way up as your business grows, but step these down over time. So the takeaway here is that time series data chunks very well. We have customers that chunk by year, by month, by week, by day, by hour. It's entirely what works for your use case. And this is important when you have big, growing time series tables. And the emphasis here is on growing because, again, that's when you're accumulating potentially infrequently read data. So the final best practice, this is the last one, is exporting data with DynamoDB Streams. So recall that we're trying to get all of last month's orders. This is kind of an analytics, business intelligence type workload. So there's two questions we should ask. Do we need results in real time, or does near real time suffice? And do we have other queries to consider? If so, perhaps an alternate data store would be better suited for this particular workload. So let's compare DynamoDB to, say, data warehousing, because this seems like a data warehousing workload, at least to me. DynamoDB is really good at real-time stuff. It's very performant, has very good random write performance, and it's got very good high availability, very good fault tolerance. Data warehousing, on the other hand, is good at bulk ingestion, sequential writes, and it's excellent at ad hoc queries. And that's really where this particular workload might benefit, because we're talking about analytics. It would be nice to have an analyst sit down and run queries against this corpus. One of the things that I've kind of been reiterating throughout this talk is that it's very important to think crisply about your query patterns when you work with DynamoDB. But that doesn't quite work here. So how do we integrate a data warehouse into our DynamoDB-based ecosystem? Well, until now, the way that you would do this is by scanning. Usually use an EMR fleet. You'd spin this fleet up, they'd scan the whole table, they'd push all that data to this data warehouse, and then you run your analytics app directly against this data warehouse. So this works. We have plenty of people doing this every day, but there's a couple problems with it. The first is that this data warehouse is going to be out of date. Every time you scan, it's fresh, but then over time, it gets staler and staler. And then it's fresh again, and it's staler and staler. So what can you do if you want fresher data? Well, you can scan more frequently. But when you dial up the frequency of that scan, there's two things that happen. One is that it costs more, because the scan consumes read capacity. The second thing is that the scan's actually less efficient, because you're walking the whole table no matter the rate of change of the items in that table. So we recently pre-announced a new feature. It's called DynamoDB Streams. It's available for preview now. It will be publicly released soon. And the way that it works is that you can turn on DynamoDB Streams for your table, and as updates, puts, or updates occur to, or deletes occur to your table, these updates are published on a stream. And then you can consume this stream and do anything you want with these updates. It's a super powerful primitive. It's like a Swiss Army knife. So some of the use cases that we see people planning to use it for are cross-region replication. We actually have a library that will do that. Elasticsearch integration. We also have a library for that. You could do cache updating. You could do complex indexing logic that's not currently supported in global secondary indexes. You can do in-memory aggregation, or you can export this data to an alternate data store. So in this particular use case, where we're trying to build up this data warehouse that's trailing behind our DynamoDB table, but minimizing the gap in freshness, we would push it to this data warehouse and, again, talk straight to that. So this is important when you need to bridge to other data stores with DynamoDB Streams. You can really tightly integrate this data warehouse into your ecosystem, and there's no more of this lag. And this is important not only when you need near real-time data, which is a point I've been beating to death, but also you need the ad hoc queries. I mean, data warehouses are still super useful. So you can tightly integrate these other data stores into your ecosystem. So in summary, we've talked about some takeaways to unlock scalability with your data model. One of the things that DynamoDB will benefit from, your usage of DynamoDB and your application will benefit from, is thinking about these things at design time. You don't need to completely front load it, but it's something to keep in the back of your mind as you're building up your application. So select keys based on queryability and uniformity. It's really the marriage of these two factors that makes a good key. Key selection is an art, it's not a science, but you can think about how you want to get at your data and how that access pattern is going to play out. Apply those same lessons to indexes. Remember, write uniformity is a min function of the table and the indexes. Avoid accumulating infrequently accessed data. Avoid it by either deleting it and archiving it or putting it in another table with table rotation. So you can really dial those down over time. And use DynamoDB Streams to do whatever you want, but one of the things you can do is export data as it arrives. So thank you very much. I really appreciate the chance to talk to you. I'm going to hand over now to Brett McCleary with Precision Exams. We will be available for Q&A after the talk out in the hall. Thank you. Thanks. Yeah, man.
All right. Thank you very much, Ben. I appreciate the opportunity you've given me to just talk a little bit about what we've done as an organization. As far as introductions go, my name is Brett McClary. I'm a Vice President of Software Development at Precision Exams. And what Precision Exams is a company that's based in American Fork, Utah, and we provide online testing software for high-stakes testing across the United States. So our product is made available as a service to the state or the districts, so high school students can get in and take exams and get certified in a variety of educational pathways. Now that's quite a mouthful. My opinion is we're a small company, we're extremely innovative, and we love working with technologies to solve real-world business problems. So one of the problems that we came up a few years ago, well, a couple years ago, was what do we do with our data? We have a lot of students coming in taking tests. We have exponential growth in our business. Where do we store this data? So what we decided to do was go with Amazon DynamoDB. We take all of the student assessment data that comes into the app servers, we store it in DynamoDB, and then we have a data warehouse process that runs. Based on what I've learned in this conference, we're going to be changing this up a little bit. But we have a data warehouse that runs. We pull the data out of DynamoDB. We transform it and insert it into our MySQL database, a relational database, where we do all of our statistics and test metrics that we collect for the students. So one of the important things that we had on our table is why did we go with DynamoDB? The answer to this question is really what I'm going to be talking about. As Ben pointed out, the data storage expands based on our needs. So testing is interesting, and there's peaks and valleys with that particular industry. So we need to be able to expand it as we need it. We also needed consistent performance under load. One thing that was driving me crazy is the more students that would hit our database, the worse our performance got. And it was like, this can't happen over time. We didn't want to have any installation. I'm done building infrastructure. I'm through with that cost. And we did look at the overall cost model, and we really appreciated what Amazon had done with their costs, and it fit really well with our business. And finally, we did a bunch of proof of concepts, and it worked really well with our ecosystem. We were able to get it into our technology stack without a lot of work. So these are the steps that we took to select DynamoDB. We found these useful, so I wanted to share them with you today. So the first thing was to know your data. So for us, we identified our hottest tables, which of course was our student assessment tables. As they were answering questions, we would write, and we also had to process stuff on the back end. Our traffic patterns were very important to us as well. We needed to understand our read and write workloads. And again, we wanted to make sure that our data size and structure was appropriate for DynamoDB in the selection. So here's a couple of our hot tables. I don't want to get too much into our domain, but I think you need to understand this to understand the rest of the discussion. This is our test packet answer table. A test packet ID is our unique identifier within our system that associates a particular test to a student. And so what we did is we created a hash key on that test packet ID. Now you'll notice that this schema is pretty simple, and we kept it that way on purpose. We wanted to make it very easy to query, and we wanted to make it very fast. The other attribute that we have is an answer JSON. What this is it's basically a JSON document that holds all of the answers that a particular student has provided. So this is what a record looks like in DynamoDB today. So this is an actual one. The ellipses that are there to show that there's additional responses that are in this particular record, and it can range between 50 to 100 depending on the particular test. So these are pretty big data documents. They're on average, they're about 10 kilobytes. Now the other hot table was our test packet response. This table is written as the student answers each question. We kept the test packet ID as the hash key. That's a very good one for us. And we introduced a range key with a test packet response ID. We have to be able to go in and find each individual response that a student has answered a question on. And then some of the other ones are timestamp, post date, and then the response JSON is the actual JSON string. This is an example of that packet. As you can see, it's very small. On average, it's 195 bytes. So this was an excellent candidate for us in DynamoDB. Then next was our traffic patterns. We have a test packet response table, which we've talked a little bit about. And this is the workload that's provided when the students answer the questions. The peak write performance that we needed was 4,000 writes per second. Now, it's pretty elastic because the heat on here is unpredictable. We couldn't really find out, well, we didn't really know when it's going to be high and when it's going to be low, because that's when the students are answering the questions. So we have an elastic provisioning put in place for about 2,000 writes per second to 4,000 writes per second. With the test packet answer, our workload was very different. It was a read workload that was being pulled from our data warehouse. So we had full control of this, and so we set it at 200 reads per second, and that makes a nice, consistent heat for us on this particular table. The big takeaway, if there's something in your process that you can control, control it. We didn't want to spend a lot of money on this particular piece of our application. And the other one is we had dynamic provisioning on those things that are very elastic. Step 2, performance testing. I wanted to make sure that DynamoDB did what it said it would do. So we went ahead and put together a testing harness for this. We have a test architecture, which you can see is pretty simple. We have some load servers, and then we also have a measurement server. We've done this, this is kind of one of our best practices internally. We've done it for years. I just want to highlight it here because it's really nice to have the load be put on the system by different servers that are actually going to be taking the measurements. We did not want to skew our measurement data. We didn't want to skew our latency data. So we separated the load from the measurement, and multiple servers did the job for us. Our objectives with our test software was that we wanted to make sure that we had an accurate synthetic workload. So we were tired of guessing, and we wanted to be a lot more systematic about it, much more scientific. So we put together a test software that would provide that for us. We had a replay engine, again, so we could run it over and over and over without any problems. And we wanted to see what our realistic models were doing against all of our partitions. So as Ben mentioned, we wanted to make sure that our keys were widespread as we ran these tests. We chose to use a framework. It's an open source framework called Grinder. I don't know how many of you are familiar with that, but it's basically designed for load and performance testing. We like using it because we can write our tests in Jython. Jython is something that if you haven't used, it allows you to import Java libraries. So we like Jython a lot. We also run it as a single Grinder process with multiple threads. And then we allow the Grinder framework to capture any of the test metrics. So they have some of those built in. And then we write a command line utility that goes through and parses those metrics that are saved by Grinder, so we don't have to continue to export them into Excel to do the analysis. We can just run the test, run our script, and we have the information that we want. Our test harness, because we use Grinder, is also very simple. Our philosophy is we don't want a lot of moving parts. We want to make sure that our measurements are accurate, and we want nothing to get in the way there. So we have Grinder, we have Jython scripts, and all of our clients that we have here are actually written in Java. We know Java has better performance than Jython. Again, we're looking at latency numbers, so we want to make sure that there's no performance issues introduced by the test harness. So each one of these clients makes a connection to DynamoDB, and it's the number of threads that run and the number of requests that each thread makes that creates our synthetic workload against DynamoDB for those to collect those numbers. While we were doing this, Ben mentioned this. I'm just going to hit on it again because I think it's really important, especially if you're looking at milliseconds. And with DynamoDB, when we were looking at it, we wanted to get down to as close as we could to what the actual numbers were. JVM tuning is extremely important. Garbage collection, as Ben mentioned, can get in the way of those measurements. So what we do is we watch that measurement server pretty closely, and when we do a measurement cycle, we make sure that we can understand what the garbage collector is doing. Heap size, again, is important. My philosophy is don't starve the JVM, but too much might get in the way. So you have to experiment a little bit with that. and basically monitor the application. So garbage collection and heap size will impact your latency numbers as you perform these tests. Analysis. All right, everything's set up. Now the fun began. So we started to run our tests, and this is one of my favorite slides. It basically, we started our test session, and this wasn't the only test session we did. We did several because I wanted it repeatable. This is just the one that I liked the best. We started out with a low provision, and this is on the test packet answer table. So this is with the larger data records, the 10 kilobytes. And so we started off at about 300 with a provisioned read capacity, and then we ran our load testing on our load servers. During this time, we let it stabilize for about 15 minutes and then took a measurement. Then we upped the capacity, waited a little bit, tuned the testing client again, and started our tests again. The interesting part about this was I felt the two things that I put arrows on. We saturated one of our load servers. So we just couldn't provide any more load, but I went, hey, I kind of like that. Let's take a measurement. So we went ahead and took a measurement there. We put another load server in our bank, and then we bumped it up to about 5,000 reads per second, and then saw what happened. Now, Ben mentioned bursting, and I just wanted to show you this again. It followed the same pattern that Ben used. It went up and then flat and then came down as it began to throttle on the back end, but I couldn't fit it into the graph, so you're just going to have to trust me on that one. But it went up to about 5,000, and it stayed there for about 5 minutes, and then it came back down. So that is how bursting worked for our test session. And during this time, I was able to monitor the CloudWatch graphs very closely. We did not have any throttling, and our get latency was very, very consistent. So I was all over it during this session. Here are the graphs that came back from our client, also the server, and a P90. So the P90 is the client latency. So what I liked about this is it actually was better than I expected. I've been looking at P90 graphs for a long time, and this I was actually expecting it to be between 15 and 12 milliseconds. It came in under that consistently. The next one there is the average client latency, which is the blue one, and that fell right in the range that we wanted as well. So it was right at like 8.5 milliseconds. So for our application, that was fantastic. And then the server-side latency was perfect. It just followed that line directly. Some nice surprises. So my background is I've been working in IT for quite some time, and I hate surprises. But I actually liked these one, and that's why I'm going to mention them here. The API documentation was accurate with regards to DynamoDB. The SDK client worked as I expected. They had solid sample code, and also there was some really nice query methods inside of that SDK client that allowed us to get access to our DynamoDB very easily. Like I said, we did not want to have a lot of spin-up time with any of this technology. It's a robust technology with a reasonable learning curve, so that's why we went with it. In summary, these are just a few things to remember. Understand data and traffic patterns. So make sure that as you go ahead and design your DynamoDB tables, your applications, a lot of the things, the best practices that Ben mentioned, make sure you understand those data and the workloads for each one of those tables. Capacity provisioning. Make sure you understand the math associated with that, especially if your packets are large, your records are large, over 4 KB and over 1 KB for writes. Make sure you understand how to provision that capacity. If you have inexplicable latencies within your app server or your testing harness, make sure you investigate the JVM, tune it, and set it accordingly. Check the throttling graphs and the performance tests on the back end as well. And then also optimize the data schema and the keys. So for us, we use the test packet ID, and that was a very good key for us. It had wide distribution, and while we were doing these tests, actually, we used real data, and we used 10,000 different student records, 10,000 different test packet IDs to get a good key distribution across all of our partitions. So keep the data table structure as simple as you possibly can. In closing, I just want to say that I am very excited to be in this industry. I love what I do. I love my job. And it's neat to have a company. This isn't a pitch, and they're not paying me to say this, but I want to say it anyway because I'm a hard customer. I'm very picky on the technology that I choose. As you can see, I look at it very closely. But it's nice to have a company come out and provide services and technologies that actually help me grow my business. I don't want to worry about the services. I don't want to worry about the infrastructure. What I want to do is get more students taking tests so I can put more money in my account. And that's really what I want to do. And Amazon helps me to do that, especially with DynamoDB. Thank you very much.